Okay, so this video is looking at example problems with verifying trigonometric identities. So I'm going to pick some ones here that I haven't done for the homework assignment. So the basic idea for identities is you have two sides of an equation and you're trying to use trig identities to simplify one side so that it's equal to the other side. So, a simple example would be something like this. And the identities we have at this point are the reciprocal identities, the quotient identities, the Pythagorean identities, the cofactor identities, and the odd-even identities. So typically if you don't have something that's squared, you're not going to use the Pythagorean identity. And if you have tangent or cotangent, you're probably going to use, you might use the quotient identities, but we don't have either one of those. So the most likely thing is to use the reciprocal identities. So the cosecant is the reciprocal of the sine. So I can replace the cosecant with over the sine, and then you can simplify that. Sine divided by sine is 1. So you get 1 equals 1, which is what we're trying to prove. Here you can't tell that they're the same, but now it's obvious that they are the same. Okay, so let's look at this one. This is the cotangent squared of y times the secant squared of y minus 1 equals 1. So again, we're going to work on the left-hand side. And when you see something squared plus or minus 1, that usually gives you an idea that you might want to use one of the Pythagorean identities. And the specific one we want to use is the tangent secant. So the original identity looks like this, but you can see that if we subtract 1 from both sides, we'll get secant squared y minus 1 is equal to tangent. So I can put that in there. So we get cotangent squared y times, instead of secant squared y minus 1, it's going to be tangent squared y. And then you can use the reciprocal identities. So the cotangent is the reciprocal of the tangent, and the tangent is the reciprocal of the cotangent. So for tangent squared y, I can put 1 over cotangent squared y. So if you have something that's squared, you can do the same thing. So 1 over cotangent, or you can have tangent is 1 over cotangent, or tangent squared is 1 over cotangent squared. And now you have the same term in the numerator and the denominator. So you can simplify that down, and then you're done. Okay, let's look at this one. 1 minus 2 minus secant squared of z is equal to 1 minus tangent squared of z. Now they look both equally about the same as far as difficulty. So if they're about the same, I'll just use the left-hand side. Again, we're going to use the same Pythagorean identity, and I can substitute z in. Just the variable is the argument. So you can see I have secant squared is equal to 1 plus tangent. So I can plug that in. For secant squared, I can plug in 1 plus tangent squared. So I get 2 minus the quantity 1 plus tangent squared of z. That's equal to 1 minus tangent squared of z. That's the right-hand side. And 2 minus 1 is 1. And minus, you get 1 minus tangent squared of z equals 1 minus tangent squared of z. You don't have to show 1 equals 1. Once you get to a point where they're the same on both sides, you're done. Okay. Let's see, secant squared of theta over cotangent of theta is cosecant theta secant of theta. So again, I'm just going to start working on the right-hand side. So I see this cosecant squared, and that makes me think that I would use one of the Pythagorean identities, the one that involves cosecant. I'm just looking in the book, is 1 plus cotangent squared theta is equal to cosecant squared theta. Now that doesn't look like really is going to help me. So then I think the reason why I didn't think that'll help me is because I'll now have two terms on the left-hand side. I've got one term on the right-hand side, so that's probably not going to work. The other option is I can rewrite both of these in terms of the reciprocal and quotient identities in terms of sine and cosine. And you're like, why would you do that if you got secant and cosecant over here? But I think it's going to work. So the cosecant is 1 over the sine. So cosecant squared of theta is 1 over sine squared. And the cotangent is the cosine over the sine. That's the quotient identity. And now if I take the reciprocal of that, so instead of dividing by cosine theta divided by sine theta, I multiply by sine theta over cosine theta. And you can see I've got sine theta up here and I've got sine squared theta, so I can simplify that down to 1 over sine theta for this term, canceling that out, get rid of the squared, 1 over cosine theta. At this point, I can take the reciprocals of these, which the reciprocal of the sine is the cosecant, the reciprocal of this cosine is the secant. So this is all left-hand side stuff, and you can see now that it's equal to what I had on the original right-hand side. So because those are the same, then I'm done. So, just because something's squared doesn't mean that it's always going to be the Pythagorean identities. Okay, let's see what I got here. So I've got secant theta minus 1 over 1 minus cosine theta is equal to secant theta. So I look at this, and somehow I've got to do some simplification. And a lot of times you can use try to transform something into a Pythagorean identity. If you've got 1 plus or minus sine theta or cosine theta. So because this is 1 minus cosine theta, I'd probably try 1 plus cosine theta. So I get that. Multiply and divide by the 1 plus cosine theta. Now, when you multiply the numerator, you get secant theta so that's first. Inner is negative 1. Outer is cosine theta times secant theta. And the last is cosine theta. And that's all divided by 1 minus cosine squared theta. Now, it may seem like it's going more complicated, but for one thing, secant is 1 over cosine. So if I replace that with 1 over cosine, and then cosine divided by cosine is 1, and then negative 1 plus 1 is 0. So the numerator I can simplify down to secant theta minus cosine theta. Okay. Now the denominator I can replace with sine squared theta. The problem is I still got two terms here, which is kind of bothering me a little bit. So I'm trying to think what I'm doing here. So that may not be the right thing to do. I'm not sure what else I would do. Let me just double check that I've done things right up to this point. So I'm multiplying and dividing by 1 plus cosine theta. So that's definitely true. And I get secant minus 1 secant cosine. Okay. Okay, so that doesn't look like it's going to work. So let's think of something else. Why doesn't it look like it's going to work? Because I got sine and secant and cosine. This doesn't look like there's an avenue. The other option I could do is I could, the secant and the cosecant, the secant and the cosine are kind of related to each other. So if I wrote the secant as 1 over the cosine, like that, actually, I think I might actually still be able to do it going down here. So what I'm going to do is I'm going to what I was thinking is if I had to take this and I could take 1 over the cosine of theta minus the cosine of theta divided by sine squared of theta. Find a common denominator here. So I'd have 1 minus cosine squared of theta. So what I've done, let me not go too many steps at one time. So I'm going to combine these two. So to have the cosine of theta, or cosine of theta here. So I have the cosine of theta here. I'm going to multiply and divide by the cosine of theta there. So I'll get cosine squared theta over cosine theta, all divided by sine squared theta. So the numerators can be combined. 1 minus cosine squared theta over cosine theta divided by sine squared theta. But 1 minus cosine squared is sine squared, so I can place that with sine squared. And then I can take this and make it into a fraction and take the reciprocal, so I have 1 over sine squared theta. These cancel out. End up with 1 over the cosine of theta, which is equal to the secant of theta, which is the right-hand side. Now there may have been somewhere early that I could solve it differently, but it did work. This kind of problem requires a little bit more skill than you might get. Okay, let's look at another one here. 1 over the tangent of x plus 1 over the cotangent of x equals the tangent of x plus the cotangent of x. So just like in the past one, what I probably would think of doing is creating a common denominator, possibly. What would that do? Let's just do it. So you'd end up with the first term you'd multiply by the cotangent divided by the cotangent. So you have the cotangent of x divided by the tangent of x times the cotangent of x. And the second one you'd multiply by the tangent of x. So you'd have the tangent of x over the tangent of x, cotangent of x. So you add those two together because they have the same denominator now. And then you could use the reciprocal identity in the denominator. So you get the tangent of x, and the cotangent is 1 over the tangent. And tangent divided by tangent is 1, so you end up with the cotangent of x plus tangent of x, which is the same as the original right-hand side, except it might have been a different order. Yeah. So the original one's a tangent x plus cotangent of x, but it doesn't matter what order you add things in. So that one works. Let's do one here. It involves a cofactor. So you have the cosine of pi over 2 minus x divided by the sine of pi over 2 minus x equals the tangent of x. So these are using what are called cofactor identities, and there's one for the cosine of pi minus x. So this, if you go back to the beginning of chapter 5, section 1, you can replace the cosine of pi over 2 minus x with the sine of x, and you can replace the sine of pi over 2 minus x with the cosine of x. So that's using these cofactor identities. And then, of course, the quotient identity says the sine over cosine equals the tangent. And there we are. We are done verifying it. And let's see what else we got here. So we got, this is the last one I think we'll do of this grouping. Cosine squared of theta plus cosine squared of pi over 2 minus theta equals 1. So this is another cofactor situation. So the cosine of pi over 2 minus theta is the sine, so I can replace that with the sine squared of theta, and then you can use the Pythagorean identity to replace the left-hand side with 1. Cosine squared plus cosine squared equals 1, and then you get the final answer. Okay, so there's a bunch of those, and you know, how do you get good at them? You get good at them by doing a lot of them. I mean, there's no easy way around it. You just have to get used to identifying situations. A lot of times if you have something squared, you can use the Pythagorean identity. If you have fractions involved, finding a common denominator, combining the two fractions, and then using reciprocal identities and quotient identities. Now the second bunch of problems are, you're supposed to verify that they are identities graphically, and if they are, then you do the same thing we did in this first group, which is verifying it algebraically. We're just doing a lot of algebra. So let me write one of these down. And these look pretty complicated. I think it's just to show, you know, sometimes it'd be a lot easier to do this graphically instead of having to go through the procedure. But they're not impossible or anything. They're not that we can't do them. So that's the left-hand side, and the right-hand side is that. Okay, so let's open up the graphing program. And we'll plot 2 periods, plus or minus 2 pi. I think that's what I have here. Yeah, actually, minus 2 pi to plus 2 pi. Okay, so what we're going to graph is the function we just talked about, which was 2 plus cosine, quantity cosine of x squared minus 3 times cosine of x to the fourth. Is that right? 2 plus the cosine of x squared minus 3 cosine of x to the fourth. So that's one function. And the other function is the right-hand side of the equation, which is the sine of x squared times 3 plus 2 times the cosine of x squared, close parenthesis. 3 plus, what is it? Oh, sine squared times 3 plus 2 cosine of x. Okay. Well, that doesn't look like they're the same. So that verify if I've done these correctly, then it's not graphically tells me that they're not the same, which that happens in a couple of these situations. It looks like I might have, well, no, I think I did it right. Sine squared times 3 plus, so what I'm going to do is pause and look at the solution manual, make sure that it is actually one that's not verified. Okay, so it's not an identity. So I was correct. What would happen is you just see one curve. Okay, so let's do another one that actually is an identity. So let me find one that actually does work, and then I'll work. Okay, so this one is going to work. Sine to the fourth of theta minus 2 sine squared theta plus 1 times the cosine of theta, so that's one side, and that'll equal the cosine to the fifth of theta. Excuse me. So let's open up our graph here. So I'm going to do it again. Sine of x to the fourth power minus 2 times the sine of x squared plus 1, the whole thing times cosine of x. So that's one function. Then I have the cosine of x to the fifth power. And you can see, I just see one curve. So it plots the red curve, and then it puts the blue curve over top of the red curve. So that is true. So now we can go back here and try to prove that it's right. Now we've already got one cosine theta, so we need to convert this into cosine to the fourth. And the best way to do that is to factor it. So we factor the sine. It's like if we were factoring x to the fourth minus 2x squared plus 1, except we're doing it with sine and cosine. So what you'd end up with sine squared of theta minus 1 times the sine squared of theta minus 1. So that'll give you that. If you FOIL this, you'll get sine to the fourth. You'll get minus sine squared theta. Another minus sine squared theta gets you 2 minus sine squared theta. And then negative 1 times negative 1 is positive 1. So there's all that multiplied by the cosine of theta. So all we're doing there is factoring. We're not using any identity. And then you can use the Pythagorean identity. So sine squared theta plus cosine squared theta equals 1. Or if we solve for the cosine squared theta is 1 minus sine squared theta. So for each one of those, I can put in the cosine squared. So I get cosine squared of theta times the cosine squared of theta times the cosine of theta. And that's supposed to equal cosine to the fifth of theta. And you can see I've got squared, first power, you add the exponents, you get cosine to the fifth of theta, which is equal to cosine fifth of theta. And lo and behold, it does work. So I did that both graphically, plot both sides of the equation. So the left-hand side, y equals the left-hand side, y equals the right-hand side. If they end up being exactly the same, then you get that. Another way you could do this to check it out is if you took the two functions, instead of plotting them separately, if you subtracted one from the other. So instead of having two equations, I got one equation, and I should just get a horizontal line, y equals 0, which I do. So that's the other way of doing it. So what I'm doing is I'm taking this original equation and I'm subtracting 5 cosine fifth theta from both sides, so I get this minus that equals 0. And if you plot that, then you just get a dead line here, flat line. Okay, so that's basically what you're doing here. Verifying identities analytically. Second bunch, plotting them to show that they are true, and then verifying they're true using algebra, just like we did in the first section.